Hello everyone, this is Mike Dowding with the SD- Physics Department, and we are continuing our video series with online lectures for Chapter 26. The last video we had an introduction to resistance and resistivity, and so to recap, the two main equations that we were using were, first of all, Ohm's law, which says that the potential that is applied to a resistor will result in a current of I. And so our battery symbol over here, which has the positive and negative nodes, connected to the resistor will result in some current that is running through the resistor in this direction, and we know it's going to be in that direction because current is the flow of positive charge. Current, there we go. The second equation that we saw during the last video was the equation for resistance. And resistance depends on two main characteristics. We have the resistivity of the material, and that is unique to the material itself, along with a combination of geometry, so length and cross-sectional area of the object. And that means we can construct a resistor by knowing the cross-sectional area of the object A, along with the length and whatever that material happens to be made of, because that's what our resistivity is going to measure for us. And then in the case of temperature, if the temperature changes, the resistivity changes. And the way that's going to occur, this was the final equation that we put together in the last video, where rho naught is the initial resistivity of the material, rho final is the final resistivity, and that resistivity changes based on a change in temperature and the unique thermal coefficient of that material. And just as rho is unique to the material itself, alpha is also going to be unique to that material. So that's the review from the last video. We now want to take some of this information and apply it to some problems. So the first one I'm going to do, this is sort of a real-world example. When I was a kid, and this is going back some 30 years, showing my age here, around the holidays, you would go and buy some lights for your house of different colors. So I'll just put 3 different colors here on these strands of lights. And usually you would get a little warning tag on the set of lights that you buy, and they would say something like, don't connect more than 3 of these lights together, or you could end up with some kind of a fire hazard. And we're going to talk about where that fire hazard comes from. So we'll make a couple of more strands of lights here. So let's say you take 3 strands of lights and you plug them into an outlet. So why are we not allowed to plug in any more? And the reason for that is because this strand of lights is really just one big collection of resistors that are all tied together in a line. The material that these cords are made out of is most likely copper, and so we would say there's a resistivity of copper. But then we have to consider the length of each wire. and maybe each wire is about 10 feet long, so that would be about 3 meters each. So that would be the length. And then you have the cross-sectional area of the wires to consider. And if you've ever seen one of these strands of lights and you've maybe cut the wire, or you've seen the wire frayed, then you know that it has an extremely small cross-sectional area. We're talking like a fraction of a square millimeter. So these cross-sectional areas are extremely small. And because of that small cross-sectional area and length of the wire, we're going to end up with a fairly high resistance value to any current that's trying to travel through that string of lights. And if you'll remember, in the last video we said that the longer the path that charge has to travel, the higher the chance that that charge is going to run into something along the way. And so what I'm drawing here is just kind of a random path of charges trying to make their way through this wire, and every time that there's any kind of collision between the charge and another atom or another charge inside the wire, that collision causes a little bit of friction, which creates a little bit of heat, and that's going to cause the temperature to go up. And as we already know, if the temperature goes up, the resistivity goes up, and the resistance goes up. Well, if the resistance goes up, then the chances of having more collisions as we pass through that wire goes up. And so it's sort of a vicious cycle here of the wire just getting hotter and hotter and hotter until ultimately it fails. And that could happen in one of two ways. Either the wire itself could melt, or, as is more likely the case, before the wire melts, the protective plastic sheathing on the wire will melt, possibly catching fire, or at the very least it could spark or arc and then catch something else on fire as a result. So that's the reason why we don't want to plug too many of these things together in a straight line, because as we do that, we increase the length of the path that our charge has to travel, and that is in turn going to increase the resistance of the entire collection of wires. Now today we don't so much have that problem anymore, because we've since taken a lesson from this. You've got enough people that have set their house on fire by doing this, and connecting too many strands of lights together. Another case to consider is, well, maybe you follow the rules. Maybe you only connect 3 of these things together in a straight line, but now you have to plug the lights in somehow. And maybe you're nowhere near an outlet. So what do? You grab an extension cord, right? And you plug that extension cord in. Well, what did you just do by applying the extension cord? You introduced more length to the path, and this is going to cause the resistance to go up again. Now, if you're ever at a hardware store or other store and you're looking for a large extension cord, typically the longer cords that are like 25, 50, 100 feet long, they're not cheap. Typically you can expect to pay upwards of 50 cents to $1 per foot for some of these good quality extension cords, and that's because the cords themselves are very thick. And the reason those cords are so thick is so that we can increase the cross-sectional area, thereby decreasing the resistance of the extension cord. And whenever you make any kind of cord thicker, that's more material that's required, and so that's going to drive the price up. Now, one mistake that I see a lot of people do is they go to the hardware store and they see these really thick extension cords with the big price tag, and then right next to it there's this bargain bin of 6-foot extension cords, and they get the idea, well, I'll just buy like 5 or 6 of those really cheap extension cords that are only $1 each. And that's a huge problem, because those extension cords, given that they're not as long, they don't have to have the same cross-sectional area or width to keep the resistance low. But the moment we start connecting these in a daisy chain, then the resistance is going to skyrocket, and that's where you're going to end up with all kinds of problems. You almost definitely blow a fuse at some point, if not cause a fire. So don't do that. Alright, the next example I want to consider is a light bulb. So most light bulbs that are out there, we're still using the incandescents in most cases. If you're using LEDs, good for you. But there are still a lot of incandescent bulbs that are being sold out there. And the way these work is we plug our bulb into a source of electric current. That current then goes through the filament. It's that little wire. And if you've ever looked at that filament, it's in the shape of a very, very small coil. And if you were to unravel that coil, you would end up with probably a meter, if not more, material in length. So there is a huge amount of length of wire, and that wire itself is extremely thin. In addition to that, it's made of a material called tungsten, which has a high resistivity. And we put all of this stuff together. We have a really large length, so we have a very small cross-sectional area and a high resistivity, which gives us an absolutely huge resistance value. And as we know, resistance will eventually cause the temperature to go up, and as this coil heats up, it starts glowing. And so it gets to the point where it's so hot that it's glowing white and it's giving off light. The problem is that these bulbs are at most maybe 3% efficient. The other 97% or so is going to be lost to heat. So for all the money that you're spending on your electric bill to keep the lights on, if you're using incandescent lights, 97 cents out of every dollar is basically being thrown away. Whereas if you switch over to some LEDs, you can get closer to, I want to say about 40%, if not higher. I'll have to double check my numbers on that. But let's go ahead and say that we have a tungsten filament. And what I'm going to do is I'm going to look up on my phone the values for tungsten. Resistivity of tungsten. Resistivity of tungsten. Didn't hear me the first time. So the resistivity of tungsten is 5.6, 10 to the negative 8 ohm meters. And then what I also need to do is I need to look up the temperature coefficient for tungsten, because once we plug this thing in, it's going to start getting really, really hot. Temperature coefficient tungsten. And for that, we're getting 0.0045. Okay, so what I want to know is if we start at room temperature, and there usually room temperature is anything between like 20 and 25 degrees Celsius, depending on who you are. But I'm going to go ahead and say that that's 25 degrees Celsius. And then, given the values for tungsten, what will the new resistance of that tungsten filament be after the light bulb comes up to its operating temperature? And so what I'm also going to do is ask my phone, what is the typical operating temperature of a light bulb? And I am getting, let's see here, 4,600 degrees Fahrenheit. Now obviously we're going to have to convert that back to Celsius. Celsius Fahrenheit conversion. So it turns out that 4,600 degrees Fahrenheit is going to be approximately 2,540 Celsius. So quite a difference in temperature. All right, well, in order to figure out the new resistance of this tungsten filament, we're going to go up to that temperature equation. And if you remember in the last video, we said that there can be some thermal expansion for given materials, but this tungsten filament is so small that there's probably not going to be that much thermal expansion in terms of the ratio. In other words, the expansion of the cross-sectional area should be pretty equivalent to that of the length. And that means we can take that equation of rho and we can estimate a similar expression for resistance. So what we have here, we have 1 plus, let's see here, the coefficient, the thermal coefficient was 0.045. That has to be multiplied by 2,540 minus 25. So we'll subtract 25 from that, and 40 minus 25, what is that, 15? So that's everything inside of that parenthesis set, and I'm going to go ahead and just get a value for that right now. 0.0045 times 25.15, or excuse me, 2515. Plus 1. Don't forget the 1. So everything that's happening inside that parenthesis set says that when our tungsten filament comes up to temperature, the final resistance is going to be 12.3 times greater than what the initial room temperature resistance was. Now right here it is important to realize that These temperature scales are technically Kelvin, but the difference in the Kelvin scale is the same magnitude as unit difference on Celsius. Alright, well, so now I need to know what was the initial resistance of that filament. So we're going to go ahead and just plug in all of these original values. And we had the 5.6 10 to the minus 8 for the resistivity. And we said that the length of that coil could be anything to a meter, if not longer. So I'll go ahead and put in a meter there. And then for the cross-sectional area, this coil can be like almost, I would say, between a tenth and a hundredth of a millimeter in diameter. And so the radius, let's just go ahead and say that this is about, we actually need an extra 0 in there. So that would be about a tenth of a millimeter. We said we wanted about a hundredth of a millimeter, so yeah, that's a lot of zeros. And then we'll go ahead and assume that the cross-sectional area of that wire is circular. And wow, this is going to have a lot of zeros in it. We have 0.00001. That has to be squared times pi. So I'm getting a cross-sectional area that is equal to, well, pi times 10 to the negative 10 meters squared. And that value is going to go in right there. So I'm going to go ahead and just invert that value right now. Times the 1 for the length, times the 5.6 times 10 to the negative 8 gives me an initial resistance value of 178 ohms. So with that said, the operating resistance of this tungsten filament is going to be 12.3 times that value of 178. About 2,189 ohms. Now, when we reach that operating resistance, one question might be, well, why doesn't the resistance go any higher? You know, shouldn't this circular pattern just keep increasing forever and ever and ever until the filament destroys itself? And the answer is it could, but we don't want it to. What we want is for that light bulb to reach a certain maximum temperature and then stop, because if the light bulb destroys itself, it's no good to us. And so what happens is, remember, this light bulb is going to heat up and it's going to start giving off a lot of heat. And so what will happen is this light bulb will eventually reach an equilibrium with the amount of heat energy or thermal energy that's being produced and the amount of heat that is able to escape the bulb. And this is it can be kind of tricky, because inside this bulb you don't have much of anything. In fact, these bulbs should be evacuated. You don't want a lot of gas in there, because as the temperature increases to, you know, something approaching the temperature of the surface of the sun, gases inside that bulb would get very hot, they would expand, and the bulb might explode. In addition to that, you don't want something like air in there or anything that has oxygen, because then that will cause the tungsten filament to oxidize. Once that happens, oxidation is a chemical process. When you change the chemical composition of a material, you change its material's properties, and so when that happens, the tungsten filament will then fail. And that's another reason why we put these inside of a bulb. People like Edison figured out that these things are not going to work exposed to air, so they had to put them inside these evacuated chambers. Alright, so that's two examples of resistance and resistivity. The main one here that I wanted to focus on was this idea of changing resistance due to temperature, but also a little bit of a public service announcement here. Don't connect too many of your strands of holiday lights together, unless you're buying LEDs. LED lights are a bit more expensive, but a couple years ago I actually broke down and bought some, and I was surprised by the warning label. Whereas these said don't connect more than 3, the LEDs said don't connect more than 30. And I don't think that's going to be a problem, because I can't afford 30 strands of LED lights. But I'll go ahead and end this video early, because the next video that I do is actually going to segue into chapter 27, and it's there that we're going to start looking at connecting multiple resistors in a circuit. Just like the capacitors, we need to look at connecting resistors in series, connecting resistors in parallel, and then we need to see what happens when we start connecting them in multiple different fashions. So until then, see you next time.